Today, we're going to tackle the first 6 multiple choice problems, non-calculator, from the Calculus AB exam from 2012. We'll see derivatives, integrals, limits, lots of good stuff. Personally, I think problem number 6 is the trickiest, so be on the lookout there. Let me know what you think. But let's dive in. Problem 1 is simply asking us to calculate a derivative of a product. So we're going to use the product rule to find dy by dx. We'll take the derivative of the first factor, x, multiply by the second factor, and then do the reverse. Take the derivative of the second factor and multiply by the first. Derivative of x is just 1. Derivative of sine x is cosine x. And now to make sure we get the correct answer, we just need to do a little bit of tidying. So we'll get sine x plus x cosine x, and we see that is answer B. Now, problem 2 is asking us to find when a function is increasing. And when you see f increasing, what I want you to think is you need to be looking for where f prime, the first derivative, is posited. So let's begin by calculating f prime of x. I'll get 300x becoming 300, and then my x cubed becoming 3x squared. Now, I notice that this is a quadratic. When I graph it, it'll be a parabola, and because the coefficient of the x squared term is negative, I'm going to have something like this. So a concave down parabola. So if I want to know where f prime, this quadratic, is positive, I'm interested in where the graph is above the x-axis. So ideally, what I need to do is find the x-intercepts. So let's just do that. I'll need to solve this quadratic being equal to 0. So if I isolate my x term, I get 3x squared equals 300. Let's cancel the 3's. And then I'll take the square root of both sides with a plus or minus. So my x-intercepts here are negative 10 and 10. So that tells me that f prime is positive between negative 10 and 10, and so f is increasing between negative 10 and 10. Answer B. Now with problem 3, if you're prepared, it's a bit of a gimme, because this integral we're being asked to find is one of our standard antiderivatives. Okay, so we can immediately, if we've got those locked in, know that the answer here is secant x plus c. But since I've got you here, let's pretend that our mind has gone blank and we do not remember that this is a standard derivative. Well, we don't need to panic entirely, because we can use some of our other techniques to jog our memory, find the answer in another way. So what I could do is I could try and unpack this integral as, well, let's write secant x as 1 over cosine x, and I can write tangent x as sine x over cosine x. Now, admittedly, this looks a little bit worse, but notice I've got those cosine x's in the denominator, so I can at least write this as sine x over cosine squared x dx. Now, if I'd given you this problem previously, when we were learning about different integration techniques, this is actually a really great example of integration by substitution. So if you're interested, I'll leave this for you to do, but we could carry out this integral by using the substitution u equals cosine x. You can see all the building blocks are there. I have this cosine x piece. When I take the derivative of cosine, I get sine x. So it's all floating there, waiting for me to work with it. If we chase that down, we'll see that indeed we can recover that same answer, secant x plus c. Problem 4 is making sure that we understand our standard derivatives and can evaluate functions. So we want to know what f prime of 1 is for this function f of x. So the 7x will become 7, the 3 will vanish, and when I take the derivative of natural log of x, I just get 1 over x. So that's the rule for my derivative. And now I just need to substitute in when x equals 1. So I get 7 plus 1 over 1, that is 8. So answer E. Problem 5 might look kind of intimidating when you first see it. It's got this kind of nasty piecewise looking function, and it's got limit notation all over the place, which can be kind of scary. But if we read what the problem says and think about it critically, we'll be able to find the correct answer, no problem. So really, we're being asked what is happening in this graph as x approaches different values. And we're being asked which statement is false. The AP loves to do this. Rather than ask for a true statement, they'll ask you for a false statement. So let's take them one at a time and see which we find to be false. So for A, we're being asked what the function is doing as x approaches 2. From both sides, it is a two-sided limit as x approaches 2. Well, in the graph, we can see that as we approach 2 from the left, and we approach 2 from the right, from above, it looks like we are approaching the function value 2. So that limit looks like it is 2, and so it exists. So this is a true statement. The limit exists. Let's do the same process for x equals 3. So as x approaches 3 from both sides, from below, from the left, and from above, from the right, you can see the graph is approaching the apex, the peak of this little mountain here. So it looks like the function is approaching the value 5. So that limit also exists. That is a true statement. Let's keep going. Let's not give up. For C, we're being asked to investigate what happens at x equals 4. Well, we can see something a bit different is happening here. As I approach x equals 4 from the left, the value of the function is approaching this value slightly less than 2. And as I approach 4 from the right, from above, the graph of the function is telling me the function's value is approaching 4. So here, this limit does not exist because as I approach x equals 4 from both sides, from either side, I get different behavior of the function. So that limit does not exist. So that is the false statement we were looking for. Now on the actual exam, because you're under time pressure, if you're confident in your answer here, move on. But since we're not under time pressure and we're looking at this together, let's look at D and E and see why they were true statements in the first place. So in D, we're looking for the behavior as x equals 5 or approaches 5. So again, we're rounding towards the top of that little hill there. So it looks like this limit equals 6. It exists. And finally, for answer choice E, the function being continuous at x equals 3, we'd already considered the limit behavior as x approached 3 from the left and the right. And all we're seeing here is that actually at x equals 3, that limiting behavior was correct. There was no plot twist at the last second where the function's value jumped away. It really did achieve the value f of 3 equals 5. So that's why we know these final two statements are also true. Okay, problem number 6, the last one we're going to look at today. This is the one that I said was kind of tricky, and it can be if you're not thinking about it in the right way. So for these problems where where we're looking at a particle moving along the x-axis, the idea is we have some particle, as time ticks on, it moves one way, maybe it changes direction, moves the other way, maybe it changes direction again, and so on. So we want to know the total distance traveled between t equals 0 and t equals 3. So that means adding up all these legs of these journeys until I get from t equals 0 to t equals 3. So in problems like this, we need to be concerned with when the particle changes direction, if it changes direction. Does the velocity change from being positive, say, to negative? So let's ask ourselves, does v of t change sign? Well, in this problem, v of t is a quadratic polynomial. We understand pretty well when quadratic polynomials are positive or negative. So let's solve where that quadratic is 0. because then I can plot a nice little graph of the parabola that I'll get. So let's factor out the common factor of t, and from the zero product principle, that tells me that either t is 0 or 6. So if I plot a graph of the parabola, I know my x-intercepts happen at 0 and at 6. Because my coefficient of my t-squared term in this case is negative, I know it will be a concave down parabola. So my graph is going to look something like this. And I guess I'm technically using a t-axis in this problem. So that is between 0 and 6. Now the good news is t equals 3 is right there, halfway between 0 and 6. So the entire length of the journey that I'm interested in, you can see the velocity is positive. So I'm never actually changing direction. So rather than this complicated journey that I have up here, what's really happening is the particle is just moving forward from t equals 0 to t equals 3. So I need to know what distance I've covered along that stretch of time. Well, I've been given the velocity function. I really need the position function to work with distance, right? Well, fortunately, I can just find the position function by finding an antiderivative for the velocity function. Okay, I could say that's the integral of velocity. So if I just undo the power rule here, I'll get 3t squared minus t cubed over 3, and I'll throw in my constant of integration just to be sure. So the total distance traveled is going to be my position at the end of my journey at t equals 3, subtract my position at the start of my journey at t equals 0. So that is simply s of 3 subtract s of 0. So let's substitute in using my rule. So I get 3 times 3 squared minus 3 cubed over 3 plus my constant of integration. You can see why I'm not too worried about that in a second. And now I will subtract the position at time t equals 0. Well, that's going to be 3 times 0 squared minus 0 cubed over 3 plus my constant of integration. Lots of things to cancel here. So I've got 0 squared is 0, 0 cubed is 0. I've got my c, subtract my c. So really, my final answer here is going to be 3 times 3 squared. That is 27. Subtract 3 cubed over 3. That is 9. So my final answer is just 18. So I hope you found that helpful. If you want to see the next batch of multiple choice problems, check out this video right here.